4, Math of Chem, Lecture A. We are going to be talking about the basics of equations and formulas today. Math that has to do with chemical formulas or reactions. So it's nothing special or fancy, it's just a different word. There are 4 main types of inorganic reactions. So these are most of the compounds that we've been working with this year, things that are not carbon-based. Synthesis, decomposition, single replacement, and double replacement are the 4 names. You should memorize those. So synthesis is going to be exactly what it sounds like. We're going to take 2 small things and put them together to make one product. This is the general formula for it. A plus B yields C. So one part plus another. They could be 2 elements, they could be 2 compounds, they could be an element and a compound. But the key is that they join together to make just one product. So 2 reactants, 1 product, synthesis. The opposite of synthesis would be decomposition. You have 1 large particle that gets broken down into 2 or more smaller pieces. So general formula, C yields A plus B. So you have your 1 small piece, something happens, it breaks apart. These could be 2 compounds, they could be 2 elements, they could be an element and a compound. The key is that 1 piece for your reactant. 1 reactant is going to be decomposition. Single replacement is always an element and a compound yields an element and a compound. So you need to memorize that. An element, and how do I know this is an element? How do I know just A is an element? 1 capital letter. And a compound, how do I know that B and C is a BC is a compound? 2 capital letters. What do we know about the first one? The first one's always positive, the second one's always negative. So I have an element and a compound producing an element. Okay. When you look at whatever this first element is, you're going to look at it and see, can it only make positive ions or could it be positive or negatives? If it could be positive or negatives, it could replace either element. Usually it's something that makes only a positive ion, typically a metal, and it's going to replace the first element in your compound. Double replacement is always 2 compounds. 2 compounds make 2 compounds. So if I look at this one, and the A must be positive and the C must be negative, and I look at the second one, and the B must be positive and the D must be negative, the only choices that I have for compounds over here are AD and BC. I can predict that because I can't put the A and the B together because you can't put 2 positives together. Like charges repel, opposite charges attract. So we just flip-flop the positive ions. 2 things are getting replaced. 2 compounds make 2 compounds. Along with types of reactions, we're going to have different classifications for the formulas themselves. So there's 2 big classifications that you need to know. Molecular formulas versus empirical formulas. So molecular formulas are how these things actually exist. So when you have water, water is H2O. It is 2 pieces of hydrogen to 1 piece of oxygen. Or sodium chloride is NaCl. 1 piece of sodium to 1 piece of chlorine. Or glucose, C6H12O6. It is made of 6 pieces of carbon and 12 pieces of hydrogen and 6 pieces of oxygen. These are molecular formulas. Empirical formula is lowest term ratio. And this is what's important. This is the only thing that you have to worry about. If it's in a lowest term ratio, if you can't reduce it anymore, it's an empirical formula. So for example, water, H2O, 2 to 1 is already a lowest term ratio. Water, H2O, molecular formula is also his empirical formula. Sodium chloride, NaCl, 1 to 1 ratio is a lowest term ratio. This would be both a molecular formula and an empirical formula. But glucose, C6H12O6, this 6 to 12 to 6 ratio reduces down to 3 to 6 to 3, 1 to 2 to 1. So this would be your lowest term ratio. That would be glucose's empirical formula. For the most part, things that have molecular formulas that are different from their empirical formulas are organic compounds. This happens to be an example of a classification that you should have learned in biology as carbohydrates. Carbohydrates, carbo, carbon, hydrates, water, typically have the empirical formula of CH2O. Carbo, carbon, hydrates, water. So carbohydrates typically reduce down to an empirical formula of CH2O. Let's look at these other guys. So water, we already said if this is his molecular formula, his empirical formula, same thing. C6H14, 6 to 14 reduces down to 3 to 7. So C3H7 would be the empirical formula of this compound. And our inorganic compounds, we typically wouldn't call them molecules anyways. We build them in lowest term ratio, 1 magnesium to 2 chlorides. His empirical formula is exactly the same. His formula and empirical formula are the exact same amount. When we write formulas and we have those subscripts below them, they apply to the element directly in front of them. So this too only goes to the aluminum. As soon as we put parentheses in, this number is going to apply to everything that's in the parentheses. So it's going to apply to the oxygen and to the sulfur. Because what this subscript 3 means is that I have 3 of these sets. But within the parentheses, that 4 only goes with the oxygen, just like our rules normally say. So there's 1 sulfur and 4 oxygens within the parentheses. The 3 to the outside means that we have 1, 2, 3 sulfurs altogether and 12 oxygens. So when I look at this compound and I count the pieces, I say that there's 2 aluminums, there are 3 sulfurs, and there are 12, 3 times 4 is 12, oxygens. This skill becomes really important for all of the rest of the math. You have to be able to count the individual atoms in your equation, or we're not going to be able to do the next step, which is balancing. Last thing we need to do for this lecture is learn how to balance chemical equations. So the first thing we're going to do is talk about what balancing means and then how to do it. Okay, so chemical equations show us the reaction. The things on the left are called reactants. The things on the right are called products. Make sure you learn that. The arrow is an action. So that arrow is telling us what happens. Reactants are the things that we start with. The arrow tells us the reaction itself. This is where the action's happening. The products are the things that we make or that we're left with at the end. Reactants, products, 2 vocab words, just learn them. The arrow shows the direction it goes. Typically we write our reactions from left to right because we speak English and that's the direction that we read. Sometimes that arrow will be backwards. If you have something and the arrow is pointing to the left, then you switch. Which are your reactants and which are your products? You're going to follow the arrow. The tail end of the arrow is the things that are getting put together. The arrow points at the stuff you make. All right, we already know these symbols from our states of matter unit. S for solid, L for liquid, G for gas, AQ for when it's an aqueous solution, and that means that your solvent is water. C means crystalline, which is basically the same thing as solid. Typically the state is not that specific. There's a difference between true crystalline solids and other solids. The state typically just uses an S, but if you see a C, it also means solid. It just means that it's in crystals. We learned about these things called catalysts in biology. In biology, you probably called them enzymes. Enzymes are biological catalysts. They're things that help a reaction happen. The cool thing with catalysts is that they're not used up. They don't change at all. So they're not a reactant and they're not a product. So we can't really write them into the left and we can't really write them into the right And when we balance equations, we don't count or pay attention to them at all. But if they want to show you that a catalyst was used, they draw it above the arrow so that you know it was used in there, but you know not to count it as actual pieces in the reaction itself. So in this reaction of magnesium burning with oxygen, making magnesium oxide, we have 2 pieces of magnesium and 2 pieces of oxygen. So over here we have 2 pieces of magnesium and 2 pieces of oxygen. This catalyst at the top is going to make it happen faster, but we don't have to count these manganeses or the oxygens on either side of our arrow. This over here, where you see the calories, we'll typically see joules. You'll sometimes see it listed just as heat. So this is telling you that heat is a product. If heat is a product, that means we're producing or making heat or releasing heat. It's exothermic. If heat is a reactant, that means you need heat, you're absorbing it, you're taking it in. That's going to be an endothermic reaction. So you can look for these hints in the equation. It will tell you whether your equation is exo or endothermic. In front of your compounds, there's sometimes these large numbers that we call coefficients. So there's 2, and it's a mole ratio, so we're going to call this 2 moles of hydrogen gas plus 1 mole of oxygen gas produces 2 moles of water. Notice there's not a number 1 drawn in here. It's kind of like x and 1x. It's just understood that the 1 is there. These are the things that we change when we balance equations. You cannot change the subscripts to get an equation to balance, because then you change what type of compound it is. The coefficients are the only things that we can change. The coefficients are the only things that you change. Only change the coefficients to balance an equation. Do not change anything else. Our equations have to obey the law of conservation. So that means however many atoms of hydrogen I start with on the left, I have to end up with that many atoms of hydrogen on the right. So typically what I would have you do is make a chart, and this is from the left side of the arrow, and this is the right side of the arrow. When I look at this equation, it says I have 2 pieces of hydrogen gas. So 2 pieces with 2 atoms of hydrogen each gives me a total of 4 hydrogen atoms. And I have 1 piece of oxygen, which is made of 2 atoms. So I have 2 oxygen atoms total on the left. Then on the right, I'm going to count the same pieces. 2 molecules of water gives me 2 times the 2 atoms in each molecule, so for a total of 4 hydrogen atoms. And then 2 times the 1 atom of oxygen in water gives me a total of 2 oxygen atoms. 4 atoms of hydrogen on the left, 4 on the right, 2 atoms of oxygen on the left, 2 on the right. These match. It obeys the law of conservation. This is a balanced equation. When you look at equations, the first thing you need to do is look for mistakes. Magnesium, metal, no problem. Oxygen, however, is diatomic. So the mistake here is that somebody forgot to put a subscript of 2. And notice that if I don't have this as diatomic, it looks like the equation's balanced, even though it's not. So you have to be careful. Up here, done correctly. Down here, not. So look for your mistakes. If you are writing equations for me and you're unsure, you're making up the symbols yourself, before you try to balance it, bring them to me and have me check to see if you form the compounds correctly in the first place. If you don't form the compounds correctly in the first place, you're never going to get the proper equation. So now, even though you see the coefficients up here, let me just show you what would happen if we make a chart. I have 1 magnesium on the left and 2 oxygens, and right now I have 1 magnesium on the right and only 1 oxygen. You're tempted to put a subscript 2 here, but you can't do that because magnesium oxide just is MgO, so we have to change the coefficients instead. That means we have to put a coefficient of 2 here. Once you do that, you have to change your chart, because now there's 2 magnesiums on the right and our 2 oxygens. So now the magnesiums are wrong. We put a 2 here. That gives us two magnesiums. Notice that the coefficients stop at a plus sign and stop at an arrow. So it only carries through to the compound immediately in front of it. All right, the last example in our notes is turning a word equation into a balanced chemical equation. So this is a skill that you should have. And it's something that you're going to be expected to be able to do on your final. So potassium hydroxide, potassium symbol is K. It has a charge of +1. Hydroxide is OH. It has a charge of -1. Combines with, that's going to be a plus. Hydrochloric acid, you can look that up. Hydrogens have a charge of +1. Chlorines have a charge of -1. If you use table K to find hydrochloric acid, it's HCl. It's already written for you. 2-form is going to be your arrow. And then we're going to make potassium chloride, so +1 and -1, and water. And you should know water, it's H2O. So if we put this all together, we have potassium hydroxide, +1, -1, just one of each, because it's a 1-to-1 ratio. Combines with hydrochloric acid, that's HCl. 2-form is your arrow. Potassium chloride, +1 and -1, so it's a 1-to-1 ratio, just one of each. And water. And you know that water is H2O. So I formed all of my compounds correctly, and now I'm going to try and balance it. So again, I would make a chart with what's on the left and the right. We have potassium, we have oxygen, we have hydrogen, and we have chlorine. On the right side, I know they don't show up in that same order, but I'm going to write them down in the same order anyways so that I can match them up easier. So right now on the left, I have one piece of potassium, one piece of oxygen. Now the hydrogens become tricky because they're in two different compounds over here. So I actually have two pieces of hydrogen and one piece of chlorine. On the right hand side, one piece of potassium, one piece of oxygen, two hydrogens, and one chlorine. When I look, these all match up. It obeys the law of conservation. This is your finished balanced equation, and you don't have to change any of the coefficients. They're just ones.